and welcome to this session. This session will discuss about Gaussian mixture models and expectation maximization algorithm. Have you ever wondered how all these different machine learning algorithms are able to effortlessly categorize the complex data into distinct groups? Gaussian mixture model is one such solution which helps to categorize this complex data into distinct groups. When GMMs, in short, a Gaussian mixture model comes into your mind, please keep these important points in your mind. It's an important clustering technique which is based on probability density estimation, and it uses expectation maximization to fit the model's parameters. So now where is GMMs used? They're widely used in machine learning, they're used in pattern recognition applications, and it's a robust statistical tool in machine learning and data science, and therefore it excels in density estimation and clustering data. As I told you, when you talk about GMMs, the first thing that should come into your mind is it's a very important or one of the very important clustering method which is based on probability density estimation. And since it is a clustering method, now there are two types of clustering, hard clustering and soft clustering. You need to remember Gaussian mixture model comes under soft clustering approach, where it is distributing the points into different clusters. Now what do you mean by soft cluster and hard cluster? K-means clustering, the link to K-means clustering I will give it in the description box. Now K-means clustering is also another clustering method which is based on hard clustering. So the difference between hard clustering and soft clustering is in K-means we have hard clustering. That means the data will be clustered into one group itself, right? Each data point will belong to exactly only one cluster. Whereas GMMs or Gaussian mixture model is a soft clustering approach where you will use probabilistic methods for distributing the points into different clusters. And the method which is used in Gaussian mixture model is called as expectation maximization method. This method is used for doing the clustering, and this method is used to fit the model's parameters to achieve the best fit. So as I said, GMM is a soft clustering method which uses probabilistic model to classify the data points into different clusters. So what you see in this figure is an example of GMM. You can see these are all the different data points that we have, and this diagram is after the clustering has been done, after the Gaussian mixture model clustering has been implemented. So looking at this, you can say these red data points are classified into one cluster, the green ones are classified into one cluster, and the blue ones as an other cluster. And this is the Gaussian distribution of the first cluster, this is the Gaussian distribution of the green data points, and this is the Gaussian distribution of the blue data points. And this example, what we see is soft clustering, which we see is an example of soft clustering. So basically what is happening here is you assign probabilities to the data points. In the sense, if you see this data point, you can say that a probability of 0.03 that this data point belongs to green, and probability of 0.96 that this data point belongs to blue. Here you can see this green point. Again, we have two probabilities. Let's say, since in this diagram I just have two clusters, okay, in this is another figure where I just have two clusters. This is the blue cluster, this is the green cluster, and you can see that probabilities are assigned for each data point, saying that this is a probability, for example this green one, the probability of this cluster belonging to green is 0.9, and 0.1 probability that it belongs to blue. So that is soft clustering, where you are using probabilistic approach for distributing the points in different clusters. Whereas in K-means it doesn't happen. We do hard clustering. We say either the data point belongs to blue or it belongs to green. So that is K-means. Now coming to how does GMM work, let's see this first figure. Okay, so here we can see that there are three clusters: blue, green and cyan. So if you look at this data point here, which is in red, right, just looking at that, as humans I can identify that this is completely in the blue cluster, right? So that means the probability that this data point belongs to blue cluster is 1 and the probability that it belongs to green or cyan cluster is 0. If you see this second figure again, look at this data point. Now you can see that it is between blue and cyan. So what you can see is the probability that this data point belongs to green is 0. But the probability that it belongs to blue is, let's say, 0.2, and the probability that it belongs to cyan is 0.8 respectively. So this is how Gaussian mixture models should show their results, or it should do the clustering. So basically the probability, or these are called as coefficients, will represent the soft assignments of a data point to a particular cluster. So now coming to the next question, how are these probabilities calculated? In Gaussian mixture model, usually the probabilities are calculated using the Bayes theorem. Okay, so we are not going into details of how Bayes theorem works here. So now coming to the next question, or just a quick revision, as I shown in this previous diagram, right, Gaussian mixture model basically has here the clusterings are modeled with Gaussian distributions. Okay, so in GMM, so Gaussian mixture model, the clusters are modeled using Gaussian distribution. So Gaussian distribution was discussed in one of the previous videos. Just for a quick revision of what is a Gaussian distribution is, Gaussian distribution also called as normal distribution. So when the word Gaussian distribution comes into your mind, you should get that it is a bell-shaped curve where the data points are symmetrically distributed around the mean value. Okay, so in this figure you can see that there are 3 Gaussian curves. So this is one Gaussian curve, and what I mean by that is this is the mean value, and on the either side the data points are symmetrically distributed. And for each in Gaussian mixture model, for each Gaussian distribution we calculate the mean and the variance, that is sigma square. And what is sigma? Sigma is nothing but the width. This was mentioned in the previous video. Sigma is nothing but the width, right? As sigma increases, the width of the bell curve will increase. For example, in the blue one, the blue Gaussian distribution, the width is lesser as compared to the green bell curve where the width is more. Okay, so that is what you see here. In the blue one, the width or the variance sigma square is 0.2, whereas in red the variance is 1.0. So as the width or the variance increases, the width of the Gaussian distribution increases. So this is about Gaussian distribution, and why I'm mentioning here is this is a Gaussian mixture model. Gaussian mixture model, the clusters are modeled using the Gaussian distribution. Now, as I told in the beginning of the session, Gaussian mixture models are based on expectation maximization procedure. So let's learn what is this. Say expectation maximization procedure is a statistical algorithm where the goal is to find the right model parameters. And you need to remember that typically this is used when the data has missing values. This is normally happen many times. This will happen when you're dealing in machine learning. There are you have huge data sets, and many times the data will be missing. Some of the data will be missing, or many data will be missing. We call these missing variables as latent variables. So this is expectation maximization is used widely in such cases, and we consider the cluster number to be unknown when we are working on unsupervised learning algorithms. So definitely Gaussian mixture model is used for clustering, which is an unsupervised machine learning algorithm, right? So since we do not know some of the values in the data sets, or since we do not have the values for the latent variable, expectation maximization algorithm will try to use the data which is existing to determine the optimum values for these variables, and then it finds the model parameters. Okay, so expectation maximization, what it will do is there will be some data which is missing, which we call it as latent variables, right? So for these latent variables, it will use the existing data. It will determine what is the optimum value for these latent variables, and then it will find the model parameters. Now, what are the model parameters that it is going to find? Like mean, variance, standard deviation. So these are the statistical model parameters that it is going to find out. So based upon this model parameters, we see is the mean is good. is the standard deviation has been achieved or the variance is achieved. If not, then we go back again, we update the latent variable, and again we find the model parameter. So it's an iterative process. Okay, so you find the missing values, you find the model parameters. If the model parameters are not up to the standard value, go back, change your latent variable, again come back, check the model parameters. So you keep doing this until you achieve a convergence point. So let's discuss about expectation algorithm in much detail. Basically, this has two steps: expectation step and maximization step. In expectation step, as I told you, we are going to guess the missing variables, that is the latent variables. And in the maximization step, based upon that missing variables, you calculate the model parameters, let's say mean and variance, that is sigma square, right? And then if it is not good, then you update again the missing variables, then again you find the model parameters. Again, if it is not up to the mark, again you update the missing variables, then find the model parameters. So this step would be repeated until you reach the convergence point. Okay, so expectation maximization, it's a base of many algorithm, not just Gaussian mixture models, but for Gaussian mixture model, this is one of the most important base upon which the model is existing. So the next question is, how does GMM use the concept, that is, how does Gaussian mixture model use the concept of expectation maximization algorithm, and how can we apply this for doing clustering, right? So the question is, how do you use GMM and EM to do the clustering? So let's find out that. So let's now see the algorithm for expectation maximization in Gaussian mixture model. So let's say the first step is we assign k number of clusters. So I have some number of points, so many points. Okay, you need to first define how many clusters are there. That is one prerequisite. So suppose I say I want 4 clusters. So you need to define that, say k is equal to 4. Now how do you decide k is equal to 4? Now that's a different topic. There are various ways like elbow method and various cases are there. That depends upon your case, which data set you're working on. Now, coming to the next step. So once you have decided k, so if you have k clusters, definitely you will have k Gaussian distributions. And for each Gaussian distribution, you will have a mean and a covariance. Okay, so let's say the means mu1 for the cluster 1, mu2 is the mean for the cluster 2, and so on. And sigma 1, sigma 2 up to sigma k, these are the covariance for the different clusters. Since I have k clusters, I have k means and k variance, covariance. Now, you need to calculate one more parameter. What is this? Sigma. So basically this represents the density of distribution. It will capture the relative sizes of different subpopulations. So basically this parameter is used to find out the size of the different clusters. So now we have found all of this, right? Now we have the number of clusters, we have found the model parameters like mean and standard deviation and covariance. We also found the sizes of the relative sizes of each clusters. Now we need to find the values for these parameters to define the Gaussian distribution. Now what we will do, we will start the expectation step and maximization step. Expectation step, where I will find the missing value. In the maximization step, I will find the model parameters, and then I will keep iteratively keep repeating this step until you get the result that you want, right? So basically in expectation step, you compute the probability of each data point belonging to a particular Gaussian component. Since now I'm talking about Gaussian mixture model, right? In the expectation step, I will compute the probability of each data point belonging to a particular cluster, particular Gaussian distribution. Okay, in the maximization step, I will re-estimate the parameters like means, covariances and component weights. I will re-estimate all this to find the maximum likelihood of the data belonging to that cluster. And if it is not up to the mark, repeat the expectation step. Okay, so the difference here is when you apply expectation maximization to Gaussian mixture model, in the expectation step, I will compute the probability of each data point belonging to a particular or a k Gaussian component, right? And then I will re-estimate these values, mean, covariances, component weights and all that. And then what is the likelihood that this data belongs to that cluster? If it is not up to the mark, repeat the step. So finally this iteration will continue until you achieve the optimization, or the optimization process will continue until convergence is reached or maximum number of iterations which you would have specified is reached. So mathematically speaking, in expectation step, let's say for each point in the data set, I will calculate the probability that it belongs to this cluster. So let's say the probability that it belongs to cluster 1 is C1, probability that the data point xi belongs to cluster 2 is C2, and so on. Now the formula for this is you have the probability of the data point belonging to the particular cluster divided by the sum of the probabilities of xi belonging to all clusters. Suppose I have a red cluster and blue cluster. The probability that the data point xi belongs to red cluster is 0.2. Then I will have 0.2 in the numerator divided by 0.2 plus 0.8, which is for the blue cluster. So that's how you calculate this value. And this model parameter is basically will tell the number of points which are assigned to a cluster divided by the total number of points. So basically it's the ratio. So coming to a maximization step, after you do the expectation step, we will now update the values. We will update the pi value, we will update the mu value and the sigma values, right? And then you also, the new density is also calculated. The new density is nothing but this pi value, right? You calculate the new density, and then you again calculate the mean and covariance. Now this is how you calculate the mean and covariance. So once you calculate that, you find whether it has reached the convergence or not, or whether it has reached the maximum iterations. If it has not reached, again repeat the expectation step. So expectation step and maximization step will keep repeating until you meet the convergence or you have reached the maximum number of iterations. Now, the main difference between k-means and GMM is in k-means clustering, for which k-means clustering video I'll put it in the description box. K-means clustering, the difference between k-means and GMM is k-means only considers the mean to update the centroid. Okay, but in GMM we consider the mean as well as the variance. And of course the very important difference is k-means will it's all about the type of clustering. K-means is hard clustering while GMM is soft clustering, which we discussed in the first session. Now let's to understand this better, let's try to implement this using the Python code. So this is in Google Colab, right? So I will not be explaining the code, just let's look into it. See, in the first part of the code, I have imported a CSV file. So this CSV file is basically going to give me some set of data points. So how the original data distribution is, I will show it in the graph. And first, I'm also building the model using k-means model so that we can see the difference. I'm also building the model using Gaussian mixture model so that we can see the difference. So now when I execute this, see, this is our original data distribution. So that means this is the original data which we have, right? So these are all the different data points. Now upon this original data, I'm going to do k-means clustering. So when I do k-means clustering, you can see that all these data points here are made cyan color, this is blue color, and here there is some kind of a problem, right? See, if I took as a human, I can say that this is one cluster, this has to be another cluster. But what has happened is here also I have green, here also I have green. So k-means clustering is not really doing a best job here for this particular data point, right? So you can see that this and this has become black and this has become another cluster. So not that good of clustering. So this was a clustering I've done using k-means. Now instead of using k-means for the same data point, I've used Gaussian mixture model, and you can see the clustering has been done in a better way, right? So this entire thing is one cluster. So basically 4 clusters have happened here. So this is a difference between k-means and Gaussian mixture modeling. As you can see, Gaussian mixture models have achieved better clustering as compared to k-means. Now let's try just quickly revise or conclude this. Gaussian mixture model is basically a probabilistic model which will assume that the underlying data is generated from a mixture of several different normal distributions, right? That's what we saw, right? So in Gaussian mixture model, each cluster will have a different Gaussian distribution or a normal distribution rather than just one single normal distribution. Gaussian mixture models will capture more complex patterns and are able to handle cases where the data is multimodal. In the sense where multimodal in the sense I will have more than one peak. right? Unimodal means the data will have just one peak. Multimodal, the data will have many peaks. So it works very well for multimodal data. GMMs have a lot of applications in density estimation, clustering, and classification. And particularly, GMMs are very useful when the data are very complex, or you have nonlinear data structures, or when it is not clear what kind of distribution it is. So to conclude, Gaussian mixture model is a probabilistic model and very useful for complex patterns. So thank you very much. Any kind of doubts, if you have, you please let me know. Please put it in the comment box. Uh, I will also give link to the K-means clustering in the description block. So thank you so much, and please subscribe to the channel.